clearly correct. So before we jump into this problem, let's recall the definition of a tree. So a tree is just any graph that satisfies these three properties. It is connected, acyclic, and the number of edges is equal to the number of vertices minus 1. And turns out you only really need to satisfy 2 of these and it'll imply the third. Check out the proof of this on Diderot. It uses some nice techniques which could be useful in the homework and on exams. Okay, with that out of the way, let's jump into the problem. So the problem states, consider the following claim and its proof. The claim, any graph with n vertices and n-1 edges is a tree. So already this claim should seem kind of fishy to you, because they're basically saying you only need this property and somehow you'll have a tree, even though we know you need at least 2 of them. So it has this proof, and our job is to explain why the given proof is incorrect. Since the claim is wrong, we know there must be something going wrong in this proof. Let's go through this proof step by step. Proof. We prove the claim by induction. The claim is clearly true for n equals 1 and n equals 2. Alright, so they're going by induction. N equals 1 and n equals 2 are their base cases. Are these clearly true? Well, let's check it out. When n equals 1, you've got 1 vertex and 0 edges. Well, there's only one possible graph that looks like that, and it is a tree. Similarly, for n equals 2, there's only one possible graph with 2 vertices and 1 edge, and it's also a tree. So their base cases seem pretty legit. Now suppose the claim holds for n equals k. So this is their induction hypothesis. They're assuming that when n equals k, so when you've got k vertices and k-1 edges, that the claim is true. In other words, then you've got a tree. We'll prove that it also holds for n equals k plus 1. So in our induction step, we want to show that it holds when n equals k plus 1. Let G be a graph with k vertices and k-1 edges. Alright, so G is some kind of graph. It's got k vertices and k-1 edges. By the induction hypothesis, G is a tree, and therefore, by definition, connected. Okay, checks out. Add a new vertex v to G, so we've got this new vertex v, by connecting it with any other vertex in G. So let's go ahead and connect v to some other vertex in G. So we create a new graph G', so this whole thing with the extra added vertex v and the extra edge, let's call that G', with k plus 1 vertices and k edges. And this works because we added 1 vertex and 1 edge, so we've got k plus 1 vertices and k edges. The new vertex we added is a leaf, so it does not create a cycle. That checks out. Also, since G was connected, G' is also connected. That also makes sense. A connected graph with no cycles is a tree. If you're connected and acyclic, you've satisfied 2 of these properties, so you've got to have a tree. So G' is also a tree. Thus the claim follows by induction. Alright, we just stepped through the whole proof, and maybe nothing stood out as fishy so far. One way you can really convince yourself that the proof must be wrong is by coming up with a counterexample. So take a moment and see if you can come up with a graph that has k plus 1 vertices and k edges, but is not a tree. Okay, this graph has 3 vertices and 2 edges, so this would be our k vertices and k-1 edge graph. Let's go ahead and add 1 more vertex, and now add 1 more edge. So this is a graph with 4 vertices and 3 edges, but is definitely not a tree. It is both not connected and not acyclic. So where exactly did this induction go wrong? How did it not catch this case? Well, what the induction was trying to do here is it started off with our small graph G. We did something to turn it into a big graph G', and the reason we did this is so that we could cite the induction hypothesis on the small graph and show that the property still holds in the big graph. The place where it goes wrong is this step right here. How do we get from the small graph to the big graph? In general, for graphs, it's going to be really difficult to enumerate all possible ways to get from a small graph to a big graph. We already saw this in the example. They assumed that the only way to get from a graph with k vertices and k-1 edges to a graph with k plus 1 vertices and k edges was to add an edge and a vertex just like this. But as we saw, there's multiple ways you could add 1 vertex and 1 edge, not just this way. So what this proof ended up doing was showing that the property holds for all graphs formed via this method, where you add vertices like this. It doesn't show that the property holds for an arbitrary graph with n vertices and n-1 edges, which is what we want to show. This can be a little tricky at first because we're so used to other induction proofs, especially ones you might have done in the past in classes like concepts. When you're doing induction on algebraic terms like summations, there are some very clear algebraic steps to get from the smaller expression to the bigger expression. But for graphs in general, it's going to be tricky to be confident that you've enumerated all ways to get from the smaller graph to the bigger graph. So instead, we recommend that you go ahead and start off with your arbitrary big graph. That way you can be confident that whatever you're showing does hold for all arbitrary larger graphs. From here, you can take a specified action to get to a smaller graph. And on the smaller graph, you're free to cite your induction hypothesis. Since you took a specified action, you can go ahead and undo that action to get back to the bigger graph and show that whatever you cited in the smaller graph still holds in the bigger graph. At first, this method can seem kind of more roundabout, since why are you starting with big, going to small, coming back to big? But it helps avoid the issue we run into when we try to go from the small graph to the big graph and have to try and enumerate all ways we could get to the bigger graph. Let's see the schematic written out as some steps. So whenever you're doing graph induction, likely you want to show that all graphs with property A have property B. You'll start off with your base cases, which are usually pretty straightforward. In your induction hypothesis, you'll assume that property A implies property B for all graphs of size less than or equal to k. In your induction step, you'll start off by considering an arbitrary graph of k plus 1 vertices with property A. Our goal is going to be to show that this graph also has property B. And we'll do that by removing vertices from this graph in a very specified way to get to a smaller graph. Then we'll show that the smaller graph also satisfies property A. And we do this so that we'll be able to cite our induction hypothesis on the smaller graph, and thus say that it also has property B. Then we can go ahead and reconstruct the larger graph and argue that property B is still maintained, proving what we want to show, that all of the graphs with property A have property B. The meat of the proof is really kept in these two steps, so don't be surprised if you're doing a lot of explaining or have some casework in this section. Check out the next problem for an example of a correct graph induction that goes through all these steps.